Thanks everyone for attending this webinar. Today we're really excited to have Whiptail on, and Chris Nichols, who's a senior systems engineer over at Whiptail, and he's going to be your presenter today and dive into this. So again, as always, please feel free to ask your questions, and we'll make sure, and I will make sure that Chris answers those. So with no further ado, Chris, can you just please give us a quick introduction, your bio, who are you? Why should we listen to you? And then let's jump into the webinar itself.
I'd love to. So I'm one of the senior systems engineers here at Whiptail. I'm really responsible for really the eastern half of the country in terms of a pre-sales perspective. Been with the company about a year. In the year that I've been with the company, we've literally quadrupled in size. So that's a testament to not only the product itself, but really the flash industry and the mainstream type of industry that it's become. So it's a really, really hot topic among a lot of customers. And it's been really interesting to see how a lot of folks have started to deploy solid state, flash, those types of technologies. What I really wanted to do today is just kind of give you a tour and a spin around the product, talk a little bit about the industry, where we fit, where we've really been focused on, and run through a few demos, including GUI demos. We'll beat the array up a little and put some load through it, and do a number of different things as it relates to a lot of virtualization topics that customers are really sort of turning to Flash as a solution and as a problem solver. So if that's it, I mean, certainly we'll address questions as they come in. I welcome you to ask them, and that's about it for the introduction, Doug. So if that sounds good, we'll get started.
That sounds great. Can you believe we already have 2 questions? Well, we'll save those for when it moves on. But we already have 2 questions, and they're not even about your bio. So this is going to be fun. I look forward to it. I told Chris in the introduction, my favorite part about all these is I'm an attendee too. So I'm really looking forward to this myself. Chris, it's your show.
Great. Thank you so much. So quick agenda. What I really wanted to do is give an introduction to Whiptail, because we run into a lot of customers that say, I've heard the name before. What exactly do you guys do? What are you involved in? Give an idea of some Flash fundamentals, right? Flash itself is this huge, huge buzzword in the industry right now. And it can be applied in a lot of different ways. It can solve a lot of different problems. But we took a very specific and calculated approach to that, and I wanted to bring everybody through that. That approach is what we call Race Runner, and it's really the crown jewels of Whiptail and what makes up the operating system for our solid-state storage arrays. So I wanted to give you a little bit of insight as to why Race Runner is really valuable. Give you a really quick, brief overview of the product sets. We've really got 2 main lines, so I'll touch on those. And slides are great, and we can PowerPoint everybody to death, but I really wanted to dive into the lab and show everybody what exactly we're talking about in terms of the product sets. So we'll go through a GUI demo, give you some really, really quick insight as to how you'd actually manage one of these things. And I say it's really quick, and that's not to say that we're going to gloss over a lot of stuff. It's really quick because it's really easy to use. I mean, there's not a lot to it. We're going to do some load generation across the array, and I've actually already got that running in the background to preload the array for a few of the other things that we're going to do. In terms of the VAI plugins that are available. So if you're a VMware customer, we'll talk a little bit about why that would be valuable to you in general, and certainly why with Flash it becomes even more so. And while we're doing a bunch of load generation, we're going to kick off a boot storm of about 300 virtual desktops. So that's pretty much the deal today. Certainly if you've got any questions about anything that we covered today, we'd be glad to answer them. So let's talk a little bit about the company. Whiptail itself is about 3.5, coming up on 4 years old now. Back in 2009, we introduced what we feel is the first 100% Flash SAN-attached, NAS-attached array. It was a multi-protocol array back then, still to this day with a 100% Flash array. We're really still the only ones in the market doing that with this much flexibility. The reason that we really picked 100% Flash is because we understood that there were a lot of different types of problems and applications that this could be applied to. We actually commercialized and standardized on MLC Flash. So if you know anything about Flash or solid state, there are really 2 main types: single layer cell and multi-layer cell. Multi-layer cell is what you really kind of find in all of your consumer electronics. It's in your phones, it's in your tablets, it's in your cameras, so on and so forth. Flash itself has some inherent problems around durability, around write performance. We picked MLC Flash even though out of the box compared to SLC, it does have a little bit less durability, but knowing that both of these types of medias are fundamentally different than hard drives, they eventually wear out over time. They've got some write performance issues versus read performance. We figured if we could solve those issues for MLC, then we could pass those cost savings, because there's a huge cost difference between MLC and SLC drives, onto our customers, and make that type of performance even more viable for a lot of customers that are looking at things like Tier 1 virtualization strategies, Tier 1 applications, things like that that typically in the past meant a very, very difficult storage architect conversation. So that's the company in itself. Where we're really focused, because like I said, flash can be applied to a lot of different types of places, a lot of different ways. There's a lot of different arrays out there today for storage that talk about some sort of SSD or flash offering. We're really focused on getting you the best performance per drive. We're getting you the best performance per power draw. So a lot of these conversations become very, very interesting when applied to flash. We're very, very focused on high bandwidth, high IOPS type of applications, extremely low latency, and right from the onset of the product, it's been a multi-protocol box. So if you're talking about fiber channel, Ethernet, 10 gig, 1 gig, InfiniBand even, all those different types of protocols are stuff that we've supported since the onset of the product. So that's made it very, very valuable for a lot of customers. It's made it extremely flexible in a lot of different types of environments. And as we'll see as we walk through a lot of these different types of workloads, the performance that we're getting is really incredible when you compare it to a typical standard storage array. Because we're really focused on MLC flash, that's brought the cost down very significantly for a lot of our customers, so that they can then start to apply these types of technologies to a lot of different types of applications. And you know, where we're really focused is that upper left-hand corner, high-performance arrays. We're not trying to be a hybrid array with a mix of hard drives and solid-state drives and make compromises either way, one way or the other, for both of those medias. We're not trying to bring on a ton of features that compromise performance. We're really kind of a standard array that uses off-the-shelf commodity hardware. We've wrapped it all together in our Race Runner operating system and delivered a ton of value for the feature set that we've got available and the performance that you're able to get out of that hardware. So when we sort of look across the industry and the data center, right, I think this is the slide that really speaks to why flash is such a prevalent conversation today. Everything in the data center over the last 10, 15 years has gotten faster, and all of those things have followed Moore's law. Applications have gotten faster by virtue of the processors. Networks have gotten faster, all this stuff, but storage has really remained stagnant. So if you're a storage guy and you're looking at a hard drive-based storage array, the really, really fast drives that are available in that array today are 10K or 15K fiber channel or SAS disks. The first 15,000 RPM drive actually came out in the year 2000, if you can believe that. So literally 12 years ago, that was the fastest storage that was available, and today that's still the fastest type of hard drive that's available. Certainly we've solved that problem in a couple of different manners from the storage array manufacturers, adding more and more cache to arrays, adding more and more spindles to arrays, and that's allowed us to really look at performance a little bit differently. But fundamentally, there's still a huge gap between what the applications could be capable of and what the storage can deliver to them. And that gap is really, really important, because a lot of applications create data, and eventually that data has to be fundamentally written to some sort of media. And if that media lags behind what your application is really capable of doing, that poses a lot of different types of architecture concerns. So where we're really looking to focus is to solve that gap between what the application could be capable of if you didn't have to wait for storage, and what the storage can actually deliver to that application. So it's a really, really interesting conversation for a lot of customers when we can kind of come in and say, what if you didn't have to wait for storage? What if you didn't have to deal with latency? A lot of storage conversations, when they turn to performance, are really around how many spindles do I have to aggregate together to get to a certain I/O number to solve my performance problem. And that's great, but at the same time, what you're really doing is saying, I've got this massive amount of capacity that I'm now throwing away because the I/O requirement of this application doesn't really tend to go along the same lines as the capacity requirement. So in other words, I'm basically sticking all these spindles together to get to this I/O number, and by doing so, I don't really have a capacity problem, because I'm throwing away a lot of capacity to get to that I/O number. And that's what flash is really looking to solve, and certainly that's where our product sets come in very, very effectively to solve and close that gap. So let's talk a little bit about the flash write process here. We've got a couple fundamentals that I just wanted to cover to make sure that everybody understands that flash is a really different animal. We hear a lot from storage array manufacturers that have looked at a hybrid approach to say, yeah, you know, I'm getting better performance because I'm adding solid state storage into an array. Really what they're doing is just kind of slapping that in and treating it like a normal hard drive. And what we've come to realize in developing 100% flash arrays, that just doesn't really work as well as it could. Right? So there's a couple different things that I wanted to make sure that everybody understands. So if I'm rewriting data on a flash drive, actually let me back up. If I'm rewriting data on a hard drive, all I really have to do is trace that actuator arm over to the specific part of that drive that has the information that I want to rewrite, find the sector, and just rewrite it. And it's a very simple process. There's really no penalty for me doing that in terms of wearing the media down or anything like that. But as we talked about, there's a finite amount of times that I can actually write to a solid state drive. So over time, that drive is eventually going to wear down. Now, this is really, really important to understand because it's a very different rewrite process. So in a flash drive, what we have is a ton of 4K or 8K sectors that are 8K cells that are laid out all over the drive on the flash media itself. Different than a hard drive, because those sectors on a hard drive really operate independently. On a flash drive or solid state media, all of those are aligned in larger constructs that we call NAND pages. Now it's important to realize that the size of the NAND page can differ from manufacturer to manufacturer, but it's generally in the order from 128K up to about 2 meg. I use 2 meg because the math's really easy, because 2 is a lot easier number to multiply out than 128 or 512K or anything like that. But fundamentally here, we've got a ton of 4K or 8K cells aligned in this larger NAND page. Now the reason this is important is because if I have a rewrite operation, the process goes something like this. So I take that entire 2 megabyte page and I read all of that out to the contents of a buffer on that solid state drive. Next, I take that entire page and I erase it, which is why they call it flash. It just flashes the entire page. Next, I'm going to kick everything out of that buffer and write it back to that NAND page, including all those red areas, which is the data that I actually wanted to write in the first place. So if you look at some of the workloads available today that's, you know, a 4K or an 8K block size, maybe like a database transaction or a VDI instance or something along those lines, we could have literally hundreds, if not thousands, of 4K or 8K write requests coming in, and I'm going back and forth and doing this process. So if I've got a single 4K write request, I'm taking that entire 2 meg page, buffering it out, flashing that entire 2 meg of data, and writing everything back, including potentially that single 4K cell that I actually wanted to change in the first place. And by doing so, I've now incurred a write penalty and worn down each one of those cells within that page, even though I only really wanted to write one single cell. So that's really the fundamental problem that we're dealing with flash compared to other types of media, because of the fact that write performance suffers and because of the fact that eventually it's going to wear down over time. So that's the fundamental problem that we're dealing with solid state, and we took a very, very marked different approach as to how we actually solve this problem with the operating system that we call Race Runner. Now, Race Runner is the operating system that runs as as the main operating system for either of our two product sets. And what it actually allows us to do is add something in that we call the block translation layer. So in a normal array, you're going to have things pass through the transport stack. You're going to pick that up via an HBA or, you know, a host sitting out there on an Ethernet network or whatnot. It's going to pass those write requests to my array. It's going to go through some sort of caching mechanism potentially, and then I'm going to pass it off to my RAID stack, which is then going to write it out to media. So if I'm treating that like a typical hard drive, I'm going to go through the same process that I just described in the last series of slides, where I have no guardrails around how I actually write to that media. So potentially I could be wearing down that media very, very quickly because of the fact that I don't understand that a single 4K write could potentially wear down a much larger footprint of data. So what we've done is instantiate this block translation layer. Now its main responsibility is really twofold. One, data alignment, and two, linearization. So what I mean by that is all these 4K writes or 8K write requests are coming in. What I'm going to do is just figure out what's actually coming to the array and make sure that as all these write requests come in, I'm going to pre-package them in the same size as the natural NAND page. And keep in mind, in the last series of slides, that was a 2 meg chunk of data. So I'm going to pre-package all the data that actually comes into the array in this alignment buffer into those same types of sizes. So lots of data could be coming in, but when I actually pass it to the RAID and to the media, it's always going to be in that full 2 meg chunk. So this gets us a couple of different things. One, it allows us to greatly reduce the wear on the drives because I'm never going back and forth and doing partial page writes. And two, it allows us to extremely accelerate write performance because of the fact that we're only doing full page writes. In conjunction with this, we instantiate a log structured file system. So if you look at the entire file system and I write blocks A, B, C, D, E, etc., and I need to go back and rewrite block A somewhere, I'm not going to go back and write it in the same spot because I'm going to go through exactly the same process that I just described in the last slides that obviously is inefficient. What I'm going to do is look for free space on the array somewhere and write block A prime somewhere else that's a completely free block. So that's going to get me the write performance back. It's going to make sure that when I actually go back and do garbage collection on the initial A block, I can just wipe it out. I don't have to worry about the contents of that. So we've done a lot of stuff around optimizing that entire process with the best case scenario for the firmware of our solid state drives, which is a lot different than a lot of our competitors. But it also allows us to greatly extend the life of the media, and we guarantee all the media in the array for about 7.5 years. And it extremely accelerates write performance. So different than a lot of the arrays out there, we actually see pretty symmetric performance between how fast we can write and how fast we can read. Typically, a solid-state array or a solid-state device is really, really good at read I/O and not as good as write I/O. And we can actually be very symmetric in those two numbers. So I know I threw a lot at everybody so far. Doug, any questions or anything like that that I can answer?
Yeah, we do have a few questions, so let's go ahead and take those. We actually have a few pretty good introduction questions too. Could you address some of the other IOPS and performance claims made by the flash industry itself?
Yeah, absolutely. And that's certainly a very interesting question because we see a lot of buzz in the industry around, huge numbers. What we tend to find with the numbers that we publish for our own products is that it's something that I can point to a couple dozen other of my customers and say, this is exactly how they got to those numbers, and oh, by the way, it's exactly the same numbers that we publish on our marketing slides. A lot of vendors go out there and try to set, maybe a spec number or an I/O record or something along those lines, and they do that by virtue of the fact that they've set up almost like a science project to get to there. It's not saying that it's not valuable to know what the upper limit of some of this hardware is, but it's not really all that useful if you can't couple it to a really standard business case. And I think if you look across all the numbers that we publish, it's very, very different in that we publish real workload numbers. It's very, very attainable, and it's something that as long as you've got the hardware in your environment to drive that amount of I/O, you're not really going to have to do a lot of reconfiguration or anything like that to achieve those numbers. It's very real world.
Great. Well, what type of workloads actually fall into your sweet spot? Do you have one? Does it matter?
We do. So a couple of different things have lent themselves very, very well to Whiptail devices. And one of the things that we really hang our hat on is the fact that we deliver better write performance than really anybody in the industry right now. And that's very, very important because of the fact that lots of database use cases are heavy read, but a very significant amount of database use cases are very, very heavily write intensive. So if you do have an OLTP application or something along those lines that has a huge number of writes that it needs to manage, we're going to be able to accelerate those very significantly. Along the same lines, and we'll talk about this a little bit later once we get to the demos, VDI is a huge proponent of massive write performance. And you hear a lot about flash coupled with VDI to solve things like a login storm or something along those lines. And that's great because it's a very read-intensive operation. But once you get to something like an antivirus event or patching or something along those lines, that turns itself into a 100% write event. So unless you can manage those writes at the same rate that you can manage the reads, it becomes very, very difficult for those applications to keep up. So that's why we really have focused on write performance for a lot of our numbers and a lot of our product sets to make sure that those types of applications are very, very valuable in coupling with Whiptail.
Perfect. How do you handle the flash write cliff?
That's a really good question and a very popular question. So as we've described, writes for solid state are a little bit different than reads because I'm going through this buffering process. And the write cliff is basically when you get to the point of having the drive exceptionally full and it's got nowhere to play a shell game to figure out where to do that next write in an open block. We do some very, very sophisticated management across the entire file system and do garbage collection across the entire array instead of just an individual drive. So if you've got something that's very, very write intensive and it's starting to really fill the array up, we're very aggressive, and we've got some best practices around just keeping a fraction of the array free, just so we've got enough space to be able to address these write concerns. But the write cliff for us, even though we publish some really, really good numbers, if we're actually at the wall at the full capacity of the array, we're still able to deliver literally hundreds of thousands of IOPS across our platforms and not be affected as much by that write cliff because of the fact that we do memory management and we do media management very, very effectively across the file system.
Very good. I have a couple more that are pertinent to what you've presented already, and then we'll let you get back into it. And then, guys, we will stick around. We do honor the hour time that we slated for this webinar, but Chris and I will stick around after and continue to ask questions. So we'll do that. So next question is, are the numbers that you quote steady state numbers? Will the speed of the array decrease over time?
So the numbers that we quote are steady state numbers, and from what we've seen, we have a very, very insignificant drop off over time. We've got a lot of arrays that we've been running in the lab for literally months, if not years at this point, and we don't see the drop off because of the fact that we do media management so aggressively. So like I said, we guarantee our drives for 7 years. In a lot of cases, we pull auto support from all of our arrays every single day, and that gives us a very good snapshot of the wear patterns that we've seen on those arrays over the past few days, few months, few years. Even the very first customers that we shipped arrays to 3-4 years ago are seeing projections above 10 years for the life of those drives. And when you're talking about solid state in the industry right now, it's one of those conversations where customers have in the past sometimes needed to replace drives every 6 to 12 months, depending on what type of application they have. And that's without any aggressive media management. If we're able to deliver that and extend that life literally 10 to 20x, that's very, very valuable for customers, and the performance of those drives follow along those same terms.
Perfect. What is the write performance for 100% random 8K OLTP writes?
So that'll really depend on the product that you're looking at. So I'll actually address that a little bit later, and if I don't get back to it, Doug, please remind me. But the performance of the array is really a function of how large you want to make it. So we've got 2 main product lines, and I'll talk a little bit about those. It starts probably as small, and I use that number kind of loosely, about 150,000 IOPS, and can go up to probably about 500 or more with that type of workload. So it really depends on how small of an array you start with, because different than some of the other typical storage array conversations you're used to, as you add more capacity with us, you actually get faster and faster, and I'll explain why that happens in a little bit. But those are the general numbers that I can kind of speak to.
Perfect. I kept the question in the queue, so I will ask it again, and you can maybe amend it or say, well, we already explained it. I'm sorry, go ahead.
No, I said great. Thanks so much.
Perfect. No, thank you. And I have one last question, then we'll let you get back to it. And where did the 2 megabyte chunks get buffered before being written to flash?
They get buffered right on the solid state drive controller itself. So on a normal drive, and let me answer that 2 different ways. So the chunk, if I'm actually talking about normal drive operation, if I've got a standard standalone drive, that 2 meg chunk will actually have a buffer right on the solid state drive itself. What we do with the race runner slide, and I'm glad I still have it up here, what we do with the block translation layer is really instantiate a buffer that's the same size as each of those drives' buffers. So if each drive has a 2 megabyte buffer that it's working with by itself, we just instantiate a buffer that is equally sized to all of those drives at the same time. So if we've got, let's say, our standard 2U array with 24 drives in it, It's about 48 meg of buffer space that we keep track of to make sure that we're doing that at an array basis and not necessarily an individual drive. So we can be very, very sure that when we actually pass writes to media, it's always in that 2 meg size for the individual drives, but it's also coupled to the RAID stripe size. So I'm not sure if that makes sense to everybody out there, but really you can kind of think of it as an analogy like the grocery store, right? Instead of putting each individual piece down the down the checkout counter, what we're doing is basically checking in the entire cart itself, and that's the transaction method that we're using.
Makes sense. And then, of course, if it doesn't make sense, ask a question, guys. So,
Sure.
Chris, let's get back into the webinar, into your presentation. Sound good?
Great. Sounds great. So we've decided we've talked about how RaceRunner actually works from a conceptual level, but this is what it really kind of looks like from a process perspective. So as all of these incoming write requests come into the array, what's going to happen is RaceRunner is then going to pick those up, and it's going to say, okay, so based on all of the writes that I've got coming in, I'm going to align them to that native NAND page size, the 2 meg block or the 128K block or whatever it is for that individual drive. And oh, by the way, that's actually a configurable parameter for us. So today we're standardized on Micron drives, and we have been for quite some time. In the past, we've used other manufacturers, and all of those have varying degrees of the NAND page size. So it's a very, very easy change for us to make, and we can be very effective in that change because it's just a tunable parameter for our operating system to figure out what that natural size needs to be to get us the best case scenario for writing to that drive. So once we align them, they basically come out looking like something like this conceptually, and then we say, okay, so once we've got all these blocks stacked up, now we're actually going to pass them to media as full RAID stripes, and that allows us to speed up the writes. It allows us to cut down the durability because of the fact that we're only passing them to the drives in a best case scenario in that full 2 meg chunk. So that's really the overview of RaceRunner, but that's what allows us to do this aggressive media management. That's what allows us to get this fantastic write performance. So let's talk a little bit about the two product sets in themselves, and then we'll dive right into the lab, and we'll show you a couple demos around what it's actually capable of. So we really got two main product lines: Acela and Invicta. Acela is a tactical 2U array. Invicta is really our strategic array for growing very large workloads, multiple workloads at the same time, and giving you a very predictable envelope for your performance growth and your capacity growth. Regardless of which of these you choose, we're really focused on a few different things. We want to make sure that you're going to be able to deliver high IOPS. You're going to get some fantastic bandwidth numbers, and all of this is going to be at extremely low latency. As I mentioned, a lot of this is almost a symmetric read-write in terms of the performance numbers that we can get out of both, because those numbers are pretty close. And typically, with a lot of storage arrays, you're talking about massive read performance numbers, but not the same type of write performance numbers. So write performance is really, really important for us, and that's what we've focused on, because with solid state, read is really easy to get. So the Acela itself, we've been shipping this array in a couple of different types of iterations since the onset of the company. And when we started shipping it, it had pretty similar specs. It was a 2U array, scales from about 1.5 to about 12 terabytes. It's all MLC flash, gets us about a 250,000 IOPS for writes, about 200,000 for reads, about 2 gigabytes a second for bandwidth. So a DVD every 2 seconds or so. All this is done at 200 microseconds of latency. So if you're a storage guy, what does that number mean, right? So typically, if you're a storage guy, a really, really good latency number on a standard storage array is somewhere between maybe 3 and 10 milliseconds. 200 microseconds is literally 0.2 milliseconds. So orders of magnitude better in terms of the latency. And that's translated for some customers to very hard revenue numbers. So if I'm doing online transactions and I've got a web store set up, that latency could mean the difference of serving thousands of customers with a 4 or 5 second time between clicks, or maybe a 10 or 15 second time between clicks. And that could mean the difference between them moving on to your competitor or completing that transaction. So it's really important to understand how some of this stuff actually dives back into the application and can give you some hard analysis as to the differences. From the onset of the product, we've been a multi-protocol array, so we support fiber channel, we support 1 and 10 gigabit Ethernet, We also support InfiniBand for a front-end connection. So a lot of our high-performance computing customers have looked to InfiniBand as a really, really fantastic 40 gig transport stack, and we're able to deliver that as just a standard interface that we support. Protocols, same type of thing: fiber channel, iSCSI, InfiniBand, file, all that stuff. We also focus on RAID protections, hot spares, asynchronous replication, all those sorts of things. It's been very, very interesting for us, and I'll move on to Invicta in a minute here, because this was really the idea of how do I get from an individual array to how do I grow that to a scalable fashion. So Acela was really, really interesting array for us because it opened the door to what's really possible if I no longer have to wait for storage. And the answer was, a lot of customers didn't actually know, because it was something they'd never actually imagined that they didn't have to worry about or could architect around. So we had a lot of customers saying, Acela is great, 12 terabytes is great, 200,000 IOPS is great. What happens if I get outside of that window, or what happens if I get outside of that envelope? And the answer was, up until Invicta was released, well, you can go ahead and buy a second one and just manage those separately. And as you see, it's not really terribly difficult to manage at all. But it didn't really give us a pattern for growth that was a strategic type of environment. So Invicta was really our answer for that. So Invicta changes the game very, very significantly in that it allows us to grow very scalable approaches. It allows us to grow both the performance and the capacity very linearly, and sets customers up for really, really fantastic performance capability. So the numbers get very, very fast with Invicta compared to Acela, which really wasn't slow to begin with. But we're talking sustained read bandwidth beyond 7.5 gig a second. And again, that's 2 DVDs a second. IOPS beyond 650,000, and if you put that into perspective, it takes probably between 13 and 1,400 15K drives to equal the performance of Acela, and that's only a single 250,000 IOP node. Going to 650,000, I mean, you're talking racks and racks of spindles to get to that type of performance. Same types of latency numbers, same types of flexibility. We've got a ton of high availability options for replication and things like that. The most interesting thing for me when I came to the company was the power conversation, though. So Acela itself only pulls 180 watts at full load, and Invicta, fully populated, pulls about 18 to 1900 watts. So to put that in perspective, it's about the same power as a hairdryer, and your Keurig at home, if you're making coffee, pulls about 1700 watts. So the difference between a standard storage array with hundreds and hundreds of hard drives and Invicta from a power draw perspective is going to be orders of magnitude different. And we've talked to a lot of customers that have literally justified the cost at moving to Invicta or Acela based on just the difference in power consumption alone with no other factors. So it's been fantastic and really interesting to see how solid state changes a lot of these conversations for those customers that are looking at some sort of green initiative or a data center consolidation perspective. So all this stuff is great, but let's actually look at what the interface is going to look like. So I will hop right over here, and in the background here, I've actually preloaded the array, and I'm running iometer to generate some load across the system. So we've got about 200,000 write IOPS happening across the system already, and that's going to be the basis upon which I layer on all the other stuff that I'm going to do today for demos and for load generation. So just to show you what kind of workload that we're actually working with here, let me close this window really quick, and we'll go to the access specifications. And for some reason, it looks like I can't edit this. So we'll stop it for a second. So what I'm doing here is actually a 100% write operation. It's 100% 4K random writes, and I'm doing about 200,000 of those across the array that we've got in our lab. So I'm going to cancel here and start that back up again. And I've got a number of VMs that I'm actually running this against. So as you can see, we're generating a couple 100,000 IOPS. We're doing about 700, 800 meg a second, still under a millisecond of latency. So it's pretty decent load that we're running against here. And I'll pop this up just so we can see a graph. For the array itself, we pop over the interface, and this is the main screen. So as you can see, we've got a running performance monitor at the bottom here, and as I float over here, you can see we've been running 200,000 IOPS for, at least the entire webinar so far. And I probably should mention that this is something that I did just to make sure that we had burned through any available cache that you'd use that you're used to on a standard storage array. Due to the process that I described earlier and how RaceRunner works, we don't really have any cache to speak about on the array. But I wanted to preload this just so you know that if we've got a load over time, we're going to see very, very steady state performance out of that. So on SSR-A, and I should mention that this is the front end, this is how it looks. Invicta itself is basically made up of 2 silicon storage routers and a number of silicon storage nodes. Now the silicon storage nodes themselves are essentially an Acela unit. There's really no fundamental difference between the silicon storage nodes and Acela. So it's a very scalable operation where if you start off with something like Acela and you need to grow your footprint from a capacity or a performance standpoint, it's very easy to migrate those into an Invicta. On the back end, these lines are really depicting our InfiniBand connections running from the silicon storage router itself, which you can almost think of like as a standard controller, but in this case, it's really only providing the aggregation points for all the individual storage nodes themselves. It's providing this GUI, and it's providing really the management structure around the storage carving and things like that. So I can drill down into an individual SSN if I want and figure out how the load's going across all the storage for each individual SSN, or I can just see all of those things running through that specific SSR. So we've got about 100,000 IOPS sitting on this SSR. I've balanced all the load across both of these. So if I click on the other SSR, I've got about the same load happening on that one as well. So pretty well balanced. The silicon storage router configuration itself, if we drill down into the network. Yep, absolutely, sure.
I'm sorry to interrupt you, but I do have one question that I think needs to be asked now. And one of the gentlemen from the audience asks, why 900 US versus, excuse me. Let me start it. 900 versus 200.
900 milliseconds versus 200, sure.
Exactly.
So 200 is measured at the storage array itself. I'm going through a fabric, I've got a couple switches in the middle of it, so that's what I'm actually measuring at my application itself. So the storage array is obviously going to be faster because I'm not transporting anything over the fabric. But that's actually what I'm seeing, 900 milliseconds at the individual servers themselves.
Okay, perfect.
Great. So, well,
let's see. Actually, he has a follow-up there. He said that shouldn't add 700.
I'd have to look at our individual workloads to see what else is actually happening on the system. But certainly, if you look at the latency that we're actually dealing with, I mean, even 900 milliseconds 900 microseconds is still very, very good performance with that many I/O hammering a storage array.
Okay, we'll leave it at that.
Okay, great. So I can drill down into the individual storage nodes themselves, and that'll basically tell me how many drives I've got in an individual storage node. We've actually got a set of fuel gauges here as well, and that tells me how much I've actually worn down an individual drive or drive set. So because we do very aggressive media management, that's something where we can actually look at to say, well, how much have we actually worn down those drives, and we're keeping track of all those stats from a heuristic perspective. If I need to, say, fail a drive or remove a drive or anything like that, it's just a simple right-click context menu, and that'll give me all the options for that individual drive. For the SSR configuration itself, this allows us to drill down into things like network settings or iSCSI settings or anything like that. We've got a few bonds set up in the system itself for both 1 gig and 10 gig Ethernet, and that allows us to do things like virtual IPs, VLANs, all that sort of great stuff. The management IP right now is on this 117.80 net. I've got a couple set up on 10 gig Ethernet to deliver all my storage traffic, but if I need to edit or modify those, it's just, again, a simple right-click context menu, and I can go down and drill into any one of those different things. Peer and MPIO settings, those are very, very simple, just to say, who is my partner in this cluster and what are the iSCSI names that I need to be aware of for that. If I drill down into the volume group and the node settings, this gives me a really quick snapshot of how much storage is actually available for each individual solid-state node or the the overall system itself. So you can see we get a really quick snapshot here, and we've got a very simple pie chart. Go to the iSCSI settings. This allows me to basically allow or disallow specific interfaces for iSCSI traffic. So again, 117.80 net is my management interface. If I need to move that to allow that for iSCSI traffic, I just simply drag and drop it down into the allowed portals, and that'll allow iSCSI traffic over that portal. Support settings is just all the auto support that we dial into that system. So once a night, it sends us some stats on what is the configuration of that system, what's the LUN map look like, what kind of interfaces do we have configured, things like that. So it allows us to troubleshoot very, very effectively, and it also allows us to look at the performance on the system to keep track of that over time, so we can provide those stats back to you. Alerting, if you do have anything go wrong with the system, it'll show up there. So I've actually kept a few of these around just so you can see what it looks like. But a couple different things as we've gone back and forth trying to get the system up. I should mention that our corporate offices are based in New Jersey, so we were affected by the storm just like a lot of other folks. But we brought the lab back up in the last week or so, and as you can imagine, there are a couple different things that came up very, very interesting fashions. So all that's great, but this is a storage system, so how do we really use it as carving storage? So I'm going to click on LUNs here, and that'll allow me to go through and enumerate all the LUNs that are already available in the system. If I wanted to create a new one, I simply click Create LUN. I give it a LUN name, give it a size. It'll pick the volume group with the most space available, and it'll enumerate them biggest to smallest. And it'll allow me to pick an individual SSR, or the silicon storage router, to run that through as the primary path. Now, the silicon storage routers themselves are all dual pathed to all the individual hosts, and either of them can pick up the responsibility for any of these LUNs at any given point in time. So it's something where if I actually lose an SSR, I get disconnected from the fabric, I accidentally kick the power cord or anything like that, those are immediately going to trespass over to the other SSR, so I don't have any downtime. So it's a very, very quick, redundant approach. But anyway, so I say create LUN. That's going to create that LUN with all of the specs that I just plugged in. And as you can see, it's right there. So now that I've got the LUN, I just need to map it to some individual host. So I click on Initiator Groups. We've got a few set up already. ESX is my backend ESX lab. I'll pop into this fiber channel for my CentOS environment that I'm doing some testing on. Just click Map LUNs. And today I don't have any LUNs mapped in there because I'm doing some iSCSI testing yesterday. But once these come up, I just say, okay, where's the LUN that I actually want to add in here? I grab it, drag it up there, and it's going to create an iSCSI or a SCSI ID right off the bat. So I say create, and that's pretty much it. So I've gone through, created a LUN, mapped it to my host, and provided that everything on my host side is connected correctly, I'm all set. All I'd have to do is refresh that HBA. NAS configuration is exactly the same way and exactly the same context menus. So we go through, we've got shares. If I need to create a new NFS share, I simply say create, I give it a name, give it a host, give it a size, pick the SSN, pick the SSR, go forth and create. So that's pretty much it from the array administration standpoint. But like I said, I've already pre-created a ton of load on the system. We've got that couple hundred of IOPS that are sitting there hammering the array. So I wanted to make sure that we make proper use of that. So as you can see, that the new NFS mount just popped up. So let's go over to vCenter and just do a couple of different things here. So we've gone through the GUI demo. What I wanted to do was really two different things. I wanted to show you what VAI allowed us to do on the individual array itself. VAI is something that we released in our last patch that we announced probably about a week and a half, 2 weeks ago. And VAI, if you're a VMware person or are familiar with the VMware infrastructure, stands for VMware APIs for Array Integration. So what this really allows us to do is offload a lot of the typical storage operations to the array. I think VMware understood that a lot of the array manufacturers had a lot of stuff that was very useful for them to offload that the storage array could do a heck of a lot better than an individual ESX host could. One of these things was something like a cloning operation. So, if I've got, certainly in a VDI perspective, if I've got lots and lots of VDI images that I'm looking to then go through and create or recompose or do any of those types of operations, it's very, very similar operations. So instead of passing all of those SCSI commands back and forth from the individual ESX hosts to the array again and again and again, what we're going to do is just tell the array, hey, look, here's the type of operation that I want you to do. You've already got this information on your storage array, so just go ahead and make me a copy of it and let me know when you're done, because you're going to be able to do that much more effectively than I can. So what I'm going to do is run through a couple of quick things here. And I'm going to go say clone this demo VM. So we'll give it a name. And we'll pop it in the demo folder there. This is my cluster. I'm going to pick an Acela data store. So it's an Acela sitting in my lab there. And the Acela is going across the fabric. So even though it's going to be pretty fast because we're going from SSD to SSD, it's still going to be, basically the worst case scenario in terms of the copy, because I have to pass all those commands over the fabric. So I say next, say finish. I'm going to go ahead and clone that. We'll see how long it actually takes. So it's a 16 gig VM. And I'll grab the start time and the end time over there. Looks like we're making some pretty decent progress here. All right, so 16 gigs copied and cloned in about 30 seconds. So now I'm going to do exactly the same thing. And I'm going to go to exactly the same LUN that I've got available for that specific VM. So I'm going to go within the same array, within the same LUN, and that'll take advantage of all the VAI code that's written into the array. So we say demo next on the cluster. We say next. And I'm going to pick the same data store as it already exists in, which is this one right here. I say next, finish, and we're done. So as you can see, there's a pretty disparate difference between the two. It took me about 3 or 4 seconds to clone it with VAI, and about 30 seconds to clone it without it. So that's the kind of speed difference that you can kind of see when the array is offloading a lot of this stuff compared to if I had to do all that stuff from the individual ESX host itself. So if you kind of think about the context of this in terms of a VDI environment or building out a virtualized infrastructure with a lot of VMs, like say a web farm or something along those lines that has a lot of similarities, it's going to be very, very compelling to be able to use that type of technology. So the last thing that I'm going to do, and I know we're running up against the hour here, is I'm going to make sure that I've still got all of that load running on the system. So you can see the IOPS are still running there. And what I'm going to do is pop back into vCenter, go over to my Bootstorm folder, which has about 300 virtual machines, and boot all of them at the same time while I'm running that 200,000 IOP load.
Sweet.
All right, here we go. So I'm going to power this on. And I'm going to start the clock here. And I've got a series of consoles set up. And these consoles are VM number 1, VM 101, VM 200, VM 300. So as this boots up, we're going to see how long it actually takes me to get a splash screen and a login screen from all these individual VMs that are starting to boot up. So as you can see, vCenter is kind of going nuts, booting up all these individual virtual machines. And I've done this a bunch over the last few days just in prep for this webinar and testing some other things out. But usually it takes in the order of probably about between 2 and 3.5 minutes, depending on what else we've got going on the lab networks. But this is something that if you kind of think about how I typically architect storage for a lot of different types of tier 1 applications, this is one of those conversations that people typically separate hardware for either something with a 200,000 IOP load or something with VDI, and never those two things at the same time. I should mention that the Invicta that we've got in the lab has 3 silicon storage nodes on it. We can grow that as large as 6. So in reality, we can have about 2x the performance of what we got in the lab right now, and it gives customers a couple of different types of advantages in that they can plan for how much performance they're going to get by adding nodes. They can go through and figure out how much capacity they're going to get right off the bat by virtue of adding those nodes. And it allows them to look at architecture in a very, very different format, because now I don't necessarily have to separate a lot of these workloads and worry about one of them starving the other for I/O. So as you can see, we've got one of these booted up already, about 1:44 into it. We've got another one that I think is coming up here, but we'll kind of talk through this and see how long it takes. But like I said, typically it's in the order of between 2 and 4 minutes. I guess while we're waiting for that, Doug, any other questions that have popped up here?
Wow, we have a lot of questions. So, as always, we want to respect the hour. I shouldn't even make these webinars an hour. I should make them an hour and a half. But if you guys want to stick around, we'll definitely stick around and answer all these questions, every single one of them. And of course, this webinar is also being recorded. But don't jump off yet, because you might have follow-up questions or more questions, and we definitely want to get through all those. So, Chris, I'll let you finish, and then then we'll wrap it up officially, and then we'll get into the questions. Does that sound good?
Yeah, that sounds great. That sounds great. So it looks like we're almost done here. We've got 3 out of the 4 booted up into the splash screen, and I'm just waiting for VM number 1, and there it is. So I'll stop the clock here at 2 minutes 49 seconds. And like I said, we've booted up 300 VMs while we're actually doing a couple of other operations and generating about 180, 200,000 IOPS on that array. So if I click back to the main configuration screen here and go to the main dashboard, that'll tell me basically what happened on the array. So I've got a bunch of I/O that continues to climb on here, but that basically gives me a snapshot of all the stuff that just happened with that boot storm. And as you can see, it was still pretty flat. So that gives you an idea of what the array is actually capable of. But it's a pretty interesting conversation for a lot of customers, because this puts them in a position where they don't necessarily have to worry about the I/O limits anymore. They're welcome to put multiple very hard-hitting workloads on the same type of infrastructure and not have to make a huge investment in floor space or power requirements or massive amounts of spindles anymore, because of the fact that we get such incredible performance from the solid-state drives. So in terms of the demo, that's pretty much all I had. I'm more than welcome to open this up for questions, but Doug, that's pretty much all the stuff that I really wanted to cover from a foundation perspective.
Well, that's Chris, you did a phenomenal job, and now I look forward to diving into these questions. But like I said, we want to respect people's time. You might have another meeting. You might want to cancel that other meeting and just continue on listening to Chris answer these questions, because this is going to be good. But to learn more information, head over to whiptail.com. Chris, any other info about if they want to learn more? Can they get an eval unit? Can they download software? If they want to learn more, if they want to try this out, what do these guys need to do?
Oh, that's a great question. So, obviously this is a newer technology. It's a very disruptive technology. And, we've certainly got a couple hundred of these boxes out in the field now. We've got lots and lots of extremely happy customers. And there's a lot of very popular workloads that lots of customers start to ask about, right? Oracle databases, SQL databases, VDI, applications that depend on those types of backends. In a lot of cases, we have no problem with identifying an application that you might want to run on this type of technology, come around some metrics for success, and put some evaluation gear at your site so you can kind of kick the tires and just make sure that it's going to perform admirably for the workloads that you want to put it against. So we've done that for lots of customers in the past. We'll continue to do it for lots of customers in the future. But that's certainly something you can get in touch with our engineering or our sales teams just to kind of talk about and figure out whether or not it makes sense for you.
Perfect. Well, with no further ado, before that, I guess, thanks everyone for attending. Now it's question time, and I have a full sheet here, or full list It's so long I have a scroll bar. So let's dive into them. You ready?
I'm ready.
Okay, first question. I'll take it from the top down. First question, and this poor gentleman's been waiting the entire webinar for this. How does Whiptail replication work? Async or sync?
So today we have async. We had gone with synchronous in the past, but what we find is that the array can't be limited by the synchronous type of replication methods because of the fact that you really have to commit that right at both sides, and people buy solid state to have fantastic performance. So if you're limited by the link between those two arrays, that puts you in a position where that's your governor. By going to an async replication method, now we're able to really kind of open up that governor and figure out how fast you really need to go. So today we've got asynchronous replication between any of our array types. So if you want to go from Invicta to Acela or Acela to Invicta, any of those types of things is acceptable to us. So it's a snapshot-based replication, which means we take a snapshot every so often, and that's a configurable parameter. And at that point, you can kind of figure out what makes the best choice for you in terms of how quickly you need to do that snapshot. What's the link between the sides? How quickly are you changing data? What makes sense for that specific schedule.
Sounds good. Here's another question from the same gentleman waiting the entire webinar here. So also, if you would like to use Whiptail as part of a SRM solution, can this be a target at the recovery site, although the SAN equipment at the protected site is from a different vendor?
So today, VMware, I believe, limits you, and I'd have to refer this to VMware just to be absolutely sure. I believe it requires you to have similar storage at both sides, and I don't think you can mix SRAs. I could be wrong about that. I haven't really played around with the Site Recovery Manager too much in vSphere 5 at all, but I think it's something that you'd actually have to have similar storage arrays. Today, we don't offer an SRA for Site Recovery Manager yet. It's definitely something that we've kicked around and talked about, but it's not something that's available today for us. Certainly as part of a disaster recovery type of environment, though, we kind of want to talk about what the goals would be at both of those sites and figure out what the best method to be able to get to those goals would be. Because we talked to a lot of customers that say, hey, look, I want a Whiptail at one side, and I want some sort of disparate storage or something else at the other side because I want the data. I don't necessarily want the speed. With the 4.1.1 release, we also announced something that we call Open Target. So Open Target allows you to replicate from Whiptail to non-Whiptail, and it's one of those things that opens up the possibilities here quite substantially because the target on the other side could be a Linux host, could be a Windows host, could be something else where you've got a bunch of different types of disaster recovery solutions that you could then architect for.
That's great. How can a centralized monitoring solution like Microsoft SCOM or Quest Software's Dell or vKernel really a fog-light monitor and correlate performance from Whiptail against workloads?
Great question. It's something that we've gotten as a very popular question over the past past few months, past couple of years. We can look at that in a couple different ways. So we've got a full API set available when we came out with the current model GUI, when we came out with the current models of storage platforms, we also wrote a very rich API base. So as part of that, we could write a custom component for some of these monitoring solutions to go in and get stats from the array. We also sent SNMP traps. So if you can pick up on those SNMP traps and bring that into your monitoring solution as a viable information source, then that's available to you too. But lots of different ways we can get that information and plop it in.
Perfect. What is the write performance for 100% random 8K OLTP writes?
We did talk about that. So like I said, it's really going to depend on what the configuration for that system looks like. When I look at something like an Acela, I'd probably guess that the performance for that is somewhere in the order of 150,000 IOPS or so. As you add nodes in Invicta, that's going to get faster and faster. So if you had a fully loaded Invicta with all 6 silicon storage nodes available to it, you'd probably be somewhere in the order of 450,000, maybe 475,000 IOPS or so for that 8K workload.
Great. Are you using MLC or eMLC? If MLC, how do you protect against a drive's RAM buffer against power loss?
Sure, that's a great question. So we use MLC drives today, and a couple of the slides that I had earlier, and I know I kind of buzzed through them pretty quickly, one of those had mention of a write protection buffer. And what we've done is actually instantiate a hardware card that looks across our entire block translation layer, and as writes come in, those get written to the block translation layer to go figure out how to place it on media, but they also get written to the card sitting there in hardware that has some memory on it. It's got some flash on it, and that's basically our protection for a number of different types of write buffer operations. So that allows us to say, you know, if we sustain any type of power failure, all of the writes that we've done over the past X number of transactions are always going to be protected. So that card itself is protected with ultracaps. You know, if that array or component loses power for whatever reason, upon reboot and upon getting power back and it goes through its boot process, it's going to read all that information back from that card, and we're off and running. So we get around that in a couple of different ways, but you know, we don't really depend on the drive itself to mitigate those concerns for us. We really do it at the array level.
Okay, next question. If you have an 8K write but no other immediate writes, is there a delay while you attempt to get to the 2 megabyte write threshold?
No, there is not. So if we have a single 8K write and nothing else going on, what we're going to do is actually pre-pad that block. So we're still writing a full block, but we've padded it with zeros afterwards just to make sure that you know, we can still fit it into the same time frame and still fit it into our normal garbage collection processes. And that also allows us to still look at the same types of wear patterns on that drive.
Perfect. Does Whiptail support snaps and clones? And if so, how many per system?
So snaps and clones are a very interesting conversation. We've been offering snapshots for quite some time. We haven't really had a lot of customers asking for clones because solid state storage is a very expensive media in itself, and they don't really want to have multiple copies of that data if they can afford not to. Snapshots today, we can offer a snapshot per individual LUN. In the future, we're obviously looking to expand a lot of different conversations around snapshots, especially as the capacity numbers go up with Invicta. And we're looking to some of our customers to help us figure out a lot of these use cases, to figure out, you know, really what makes the most sense to plug some of these conversations in, and how do we want to really look at that across our application layer stack and the use cases that customers are going to. So in the past, you know, the customers that I've worked with haven't really use snapshots. We certainly offer them. We certainly have a lot of different types of ways that we can look at the GUI and do them. But we haven't really had a lot of customers using them because of the fact that, you know, either the data changes much too quickly and it gets very, very stale, or, you know, it's something where they're just using it as really almost a read cache. So they've got, let's say your VDI instances have a base replica, and that replica is really getting hammered by a ton of I/O, but it doesn't really change all that often because that's your base image and your gold standard. So you don't really need to snapshot that, and you don't really need multiple copies of it. So it's been an interesting conversation, something we're certainly going to explore in the future to figure out how we can best serve our customers for a lot of those different types of conversations. But I haven't really had a huge need for it so far.
Perfect. I love this next question. I like the code. Could I pull info from or configure Whiptail via an API or with PowerShell at the appropriate? Oh, period.
Yeah, and the answer to that is absolutely yes. So with the latest code release 4.1.1, which we offered a press release about last week and started to advertise, along with that release came our full API stack. So anything that you just saw me do in the GUI, with some additions actually, you're able to do through the API stack and through through a CLI interface.
Perfect. And the next one starts off with thank you very much. And Chris, I definitely extend that also. I think you've done a great job, but we have more, so it's not over. Could you touch upon multi-tenancy? I can't spit that word out.
Multi-tenancy support, absolutely. It's a very, very interesting conversation once you get to very, very large performance areas. Our take on multi-tenancy is the fact that because you've got a practically limitless amount of I/O that we can deliver on the back end for the storage system, it's not as important to you to be able to get in and turn a bunch of knobs and switches to say, this application gets this many I/O, this other application gets this many I/O, and we want to make sure that neither of them starve each other. And as you just saw, I kicked off a boot storm of 300 VMs while delivering a 200,000 IOP workload. Neither of those things are really all that much to sneeze at, and together it's pretty surmountable. If we get into something like Invicta that goes above 650,000 IOPS, that's something where we very rarely see a lot of applications scratch the surface of 50, 100, 150,000 IOPS. So if you've got multiples of that type of performance available to you, it's not as important for you individually to go in and manage that neighborhood relationship between all those individual applications, because of the fact that you've got virtually limitless I/O against it, and it changes the conversation pretty significantly.
Perfect. How does high availability in VR work with Whiptail?
Yep, absolutely. So we've touched on this a couple times already, but I'll just make sure that everybody understands it. So from a disaster recovery perspective, we offer async replication. So that's a snapshot-based replication. You can have an Acela at one end, an Invicta at the other end, or vice versa, 2 Invictas, 2 Acelas. Or as I mentioned, we've got an open target strategy as well that goes to Windows, a Linux, other types of storage on the back end. So it doesn't have to be like for like. So depending on what the goals are of that disaster recovery application or that disaster recovery design, there are a lot of different ways we can address DR and replication.
Perfect. Next question. We're getting there. How are current Whiptail customers providing data protection around the arrays?
That's largely a customer by customer conversation. It really depends on the use case of the data on that array, and it really depends on what they're comfortable with for their typical backup strategies. Solid state doesn't have typically the huge capacity concerns that you would have on some of your other storage arrays. So in a lot of cases, we're using a lot of the application layer tools to orchestrate that type of backup. That being said, we just talked about replication. We've got a couple of different ways we can get around backup and disaster recovery, but by far and wide, our customers are looking at the application layers to be able to provide them that backup strategy.
Perfect. The next question, and this might be taken out of context, so it just says thin provisioned with a question mark?
Yep. So I think what they're asking is, whether or not we're able to deliver thin provisioning.
Sure.
So depending on how you actually configure that storage and what you're looking at, if you look at something like a VMware environment, the default is really thin provisioned. We today really thick provision those volumes for something like a Windows box or something along those lines. But in the future, we'll definitely look to expand that functionality and offer things around thin provisioning. What we find with a lot of our customers, because we've asked them a few different times as to whether or not that would be valuable for them, and in a lot of cases the answer is, well, solid state is a little bit different animal than my general purpose storage. So what I really want to do is do some hard planning around what actually needs to be on tier 0 in solid state. And to be able to do that effectively, I want to thick provision everything at the beginning, because now I know exactly what I'm getting into, and I can manage my application growth a little bit more manually. In the future, as things change, we get to larger capacity conversations with Invicta, things like that. That's absolutely going to be something we address with our customers. But today it hasn't been enough of a widespread conversation for us to add that into the feature set. But certainly something on our roadmap.
Cool. Can you create a LUN across SSNs?
You can. Yep. So the question, and I probably should have thought about this earlier too, and typically this is something that takes me an hour and a half, maybe sometimes 2 hours to go through the full product feature set. So we've got a couple of different options around how we actually create storage on an entire Invicta cluster. One of which is the idea of mirroring, which says if I've got 2 or 3 or 6 silicon storage nodes, I can take a LUN on one of them and mirror them down to the other. Now the interesting thing about that is the fact that the silicon storage router at the top itself really is responsible for that relationship. And it ends up being a RAID 1 construct. You can almost think of it like that. So in other words, when I write to a LUN, I'm really writing to both of those silicon storage nodes, the SSNs, at the same time, which means I get 1x the write performance, but then I also get 2x the read performance back, so just like a typical RAID 1. So that means I can double my read performance for a given LUN, which could be very, very valuable in a lot of situations. We also have the idea of stretching across multiple SSNs, and we've got the ability to do that for a couple different reasons. One might be performance, one might be capacity, but yes, absolutely.
Perfect. What is the cost per gigabyte for Accelera and Invicta?
Doug, it's always one of those conversations we get into.
I knew it.
I'm the engineer. I don't deal in pricing, unfortunately. So
Oh,
what I'd probably usher you to do is definitely get in contact with your Whiptail sales team and kind of have some conversations around that. It really depends on how big the environment is going to be, how large that system is eventually going to be. But you'd be surprised. I mean, we've got some very effective bundles that start at not that much money, and it can be very, very surprising as to how much the product actually costs.
you bet. I always told people that pretty much the same answer. Hey, I'm an engineer. I don't buy product.
Yeah,
I don't have
I just
any
play with
clue
it.
what it
I just
costs.
play with it in the lab and break it.
That's exactly right. So, but it's a good question, and that's one of those. Please reach out to the Whiptail guys, and they'll get you the salespeople, and they'll get you more information about costs. But I had to ask, right?
Nope, not a problem. Not a problem.
Okay, when you detect a drive going bad at HQ, what is the procedure to replace it under service? You mentioned 7 years service, hot swap, and then send on drive back, standby drives, etc.
Yep, we've got a couple different options for that. So obviously, if a drive fails, that's something that's going to notify us immediately. A majority of our systems we actually sell with a cold spare kit, so you're going to have a spare drive on hand anyway. But if not, we'll have one to you. We've got a fantastic support system now that actually offers us 4-hour support, really across the globe for, in some very specific exceptions. But lots and lots of countries, we've got an extremely great support team. If the drive goes bad, it's a hot swappable drive, and it sounds like a typical storage conversation, right? I'm going to pop open the front bezel, I'm going to grab the drive that's blinking bad at me, and I'm going to take it out and put the new one in, and it's just going to automatically rebuild and make that new drive the spare. Honestly, in the solid-state drive world, that's actually a differentiator for us, if you can believe it. Not everybody goes through, hot swappable drive method. Not everybody has a standard form factor for a 2.5-inch drive. So we feel that we're probably better positioned for data center serviceability for something like that. If we do get a drive that fails, our support team will notify you immediately as the call comes in. You may or may not have picked up on that already if you've got some alerting internally. The system itself can send out an alert for your standard alerting system, or send you an email. I've got a couple different options there. If you do grab that drive from your cold spare kit and you put it in, we'll just ship you a next day drive. So lots of different options around how that support method and model can work.
Perfect. And what is the max LUN size?
So the max LUN size will really be dependent on how big of an array you buy. If you've got, say, a 1.5 or a 3 terabyte, the max LUN size can go up to the maximum size of that array. As the array gets larger and larger, your max LUN size will grow and grow. So, if you want to get, say, a 10 or 20 or, in theory, a 72 terabyte LUN, you're more than welcome to do it. Obviously, there are design considerations around that, but you can get very, very large pools of data and very large LUN sizes. The question I always come back to with customers is, just because you can, does that mean you should? Right? So how are you planning on backing that up? What is your data protection strategy around it? Things like that. So even though the array itself might be fine, what happens if your file system corrupts that? How are you going to get a massive amount of data back? So it's a very interesting conversation. We can certainly do very large LUN sizes up to the upper end capacity of the array, but we always want to have that gut check conversation with the customer to figure out what they actually want to use it for and what the best method of architecting that might be.
Perfect. So how do we see if there's a rogue server or troubleshoot, and I love this, the Whiptail?
Troubleshoot the Whiptail, sure. So obviously we've got a fantastic support crew, and they work tirelessly day in and day out servicing our customers and help them in a number of different ways. So if you do have a rogue server, or you have a problem with Whiptail and you're looking to kind of troubleshoot it, give us a call. We'll be happy to walk through that with you. Even if it's not our problem, we're going to make sure that we set you right and we make you whole in terms of helping you determine that it's not Whiptail. And if we've got experience around what you're actually looking to do, we have no problem helping you out, right? So it's going to be something that I'd strongly urge you to call our support team. But then again, it's a very, very simple interface. There's really not a lot to it, as you saw. So that also goes without saying that there's not a lot of stuff that you can potentially really screw up. A lot of other arrays, if you've got multiple drive types, multiple RAID sets, there's a lot of knobs and switches that I could accidentally throw. With us, we've got one drive type, we've got one RAID set, and we can go back and forth and give you a very simple configuration. If you do have questions around host connectivity or anything like that, give us a call and we'll walk you through it, and I'm sure you'll be really, really happy with the experience.
Troubleshooting the Whiptail. Is your VAI integration for block NFS or both?
Today it's for block. In the future it will be for NFS, but a majority of our customers today run block. So the engineering efforts were definitely focused on block. So for today, block. Stay tuned in the future for NFS.
Wow, this is the next question's a long one, so you're going to test my reading skills here. If you're using the SSDs for buffering and you use RAID, I assume you're using the full stripe writes. Therefore, you've got 12 megabytes to storage somewhere before you write the data to all SSD controllers. Does this get held in the SSR? And if so, how? Is it persistent if the power is lost?
So this question is around how do we really protect the data in flight for our block translation layer. We talked about this a little bit earlier with the hardware solutions that we've got to make sure that as data comes through the block translation layer, it also lands on that hardware card that protects us against any type of buffer. Right, so if you kick the power cord out or anything like that, all that data in flight getting reorganized and repacked by the block translation layer is always going to be protected. And once the system boots back up, it's going to replay that log and figure out what exactly it may or may not have lost, and make sure that all those writes eventually end up on your media as part of that boot process.
Perfect. So this must be a follow-up question. So are you saying from the host perspective, around 1 millisecond response times are considered great OLTP Oracle SQL performance for Whiptail arrays? They sound great to me.
Yeah, I mean, those are really, really fantastic response times. In some customers, we've seen a lot better than that, right? And I'd love to say that I've got a perfect lab, but the fact of the matter is, we brought it back up last week after shutting it down for Hurricane Sandy, and as labs will do, right? You've got a lot of stuff that doesn't come back up exactly how you'd like to. So this was kind of a demonstration just to kind of kick the tires and show you exactly what's capable from a broad sense. We could certainly do a lot of tuning and get those numbers much better, and we have in a lot of customers. And that's something that I'd probably urge you to look at if you've got that type of workload that you really want to see what the upper limits are. And you've got a very valid use case for introducing SSD. That would be a perfect use case for one of our evaluations to get on site and just show you exactly how fast that might be able to go for you.
Perfect. We still have more questions, and you know what's amazing? We've lost a few people, but not many at all. So let's keep on going. How do you differ from pure storage, all MLC arrays?
So the competition question we get quite a bit, right? Because we're in there and in the trenches with a lot of other players in the field. Where we really differentiate from pure, I think, is the upper limit of performance. I haven't seen hard and fast numbers for pure, but I've talked to a few folks that have tested our array and back-to-back with a pure array. And we haven't lost for write performance numbers yet. We haven't lost for read performance numbers yet. Especially if you look at something like Invicta, that scales much larger than anything that I've seen introduced from Pure so far. That's not to say that they don't have a great product, because it absolutely does do a lot of very fantastic things for customers, and we've talked to a couple customers that are very happy Pure customers. But I think, when you look at where we're focused versus where Pure's focused, Pure is more of a general purpose solid state storage array, in my opinion, where we're really going after the upper echelon of performance considerations and really top tier, give you the most I/O you can possibly generate types of applications.
Perfect. The next one's not a question, but I want to read it. I will be online until Q&A is complete. So, and we will too.
Perfect.
How do you gauge wear? What is the type of lifespan or the SSRs? If they both fail, what's the recovery time?
So if both of the SSRs fail and we boot the array up from a cold start, we're talking about probably 10 to 15 minutes. Sometimes it's quicker than that, but I'd like to give you the upper limit of that as opposed to the lower limit of that. So probably about 10 to 15 minutes if you have to boot an array up from a cold start. The wear question, we talked a little bit about in the past. We actually bump over to the interface again, and on the individual SSNs, we've actually got this fuel gauge, and we keep stats around the wear patterns. So we can tell you exactly how far the drives have worn down, and we can tell you how long they're going to last based on the wear patterns that you've actually uncovered as you run the array. So it's not a canned answer for everybody, because everybody's workload is different. But once we actually get some pattern data about what you're actually running for an application workload, we'll be able to tell you exactly how long the drives are going to last. Typically, like I said, we guarantee them for 7 years, 7.5 years. I haven't seen a customer yet that didn't go well beyond that in terms of the projections that we made for the solid-state drive life.
Perfect. How many SSRs can front end in Invicta? Always 2?
Always 2 today. Yep. So Invicta today is designed with the 2 SSRs and 6 shelves behind them. Whether or not we're going to go to a different method, I don't know. Certainly it's something that we want to keep ahead of a lot of the trends. So I think as you watch Whiptail, certainly we'll look at better performance numbers, expanded capacity numbers, all that sort of stuff. But today, this is what Invicta is designed around.
Perfect. What components are hot swappable? Are software and hardware upgrades non-disruptive?
So the components in the boxes that are hot swappable are really the drives, the power supplies, and that's pretty much it. So you can get around bringing components down, bringing SSRs down, all that sort of stuff in a lot of different ways. We talked about the idea of mirroring data. So if I had to bring an entire SSN down, I could just go through and figure out which LUNs were on that SSN and then just mirror them to another one, make sure all the data ends up on that other LUN, and take that SSN offline. If I need to take either of the SSRs offline, that's also something that I can just pull the plug on, and it's non-disruptive to my hosts. A lot of different ways we can work around system upgrades because of the fact that we really kind of do a rolling upgrade through the SSRs and reboot them one at a time. So obviously we want to plan for a downtime where you've got minimal activity if possible, but certainly a non-disruptive upgrade is certainly something that we try to strive for in almost every single service pack that we do. I'm not going to say that every single one of them is going to be non-disruptive, because I think any storage manufacturer every now and then has one that causes you to reboot the array. But I can't remember the last time that we actually had one that required that.
Sounds good. And I think we addressed this, but this is a great question from a good friend. So vSphere replication.
vSphere replication. I guess I'm not exactly sure what we're kind of looking at for replication method. If you're backed by a vSphere environment, we certainly have replication methods on the array itself to basically pick up everything that the array sees. But I'd probably need a little bit better context around what exactly we're looking at for replication there. While we're on the vSphere subject, though, I will say that we also have a vCenter plugin as well. Something that I didn't show today, but we certainly have available to say, here are all the Whiptails available in the environment. Go through and automatically configure them. Do some other stuff. Configure everything to best practices from our perspective, and make sure that that's pretty seamless in your vSphere environment.
Perfect. And here's the next question also, and it might have been maybe a follow-up to that question or part two, or maybe hit enter too quick. Cannot do array replication, but can you use vSphere replication?
So I guess I mean I haven't played around with the vSphere replication myself, so I, I want to make sure that we defer that. So if you do have specific questions on it, feel free to reach out to the Whiptail sales team, and we'll get you a much more specific answer. But if you're using replication at the vSphere layer, that my thought is that becomes agnostic to whatever storage is behind it. So if the question is something like maybe around a Veeam or vSphere types of replication that happen at the vSphere, the ESX layer, we're really not going to care about that because of the fact that you're doing it at a layer above where we're really managing.
Perfect. What kind of language can query the Whiptail API XML?
It is an XML API. So if you've got something that can query an XML API, then you're all set.
Cool. Does the NVR RAM card have a performance impact?
It does not. So all the numbers that I talked about today are including that card.
Perfect. Let's see if we can stump you, Chris. You haven't been able to yet, so we'll keep going. Only a few left. Can the array support multi-link for higher bandwidth I/O? Example, Etherlink, etc. I'm curious about scaling out the links from a single 10 gigabyte link to perhaps 20, 40 gigabyte link.
Sure, and that's something that I probably should have been a little more specific when I walked through the interface. So under the network settings here, and the answer is absolutely yes. So if you actually edit one of these bonds, this is my 10 gig bond, you can see a bunch of modes here. We've got round robin, active backup, LACP, which is I think what we're getting at with that question, and active load balancing. So we've got a couple different bonds that we can set up, and when I actually look at the devices for that bond, what you see is the IP address for the bond itself, and then the two slaves. And right now I've got two 10 gigabit interfaces, and we can certainly expand that and give you more, but we can manage that entire virtual bond with multiple interfaces in the back to aggregate performance out of it. So absolutely yes.
Perfect. Let me start over. Storage considerations. Let's say going from traditional spindles to the Whiptail.
So it's really a conversation around, for us, if you're going from traditional spindles and you're migrating that to Whiptail, we really just want to understand what the capacity limits are in a lot of cases, because when you go from standard spindles to Whiptail, the performance the performance acceleration that you get is really, really orders of magnitude better. As you can see, I was running a couple 100,000 IOPS in the background for my array, and that's the equivalent of probably 1,400 hard drives, right? So it's something where if a customer's coming from a spindle-based configuration, we just want to understand what the capacity is that they require for that application, and with very, very few exceptions, we don't really even have a conversation around, what is the upper I/O limit that you're looking to hit, because in reality, it's probably not going to touch what the Whiptail is actually providing you in many, many cases. If it does, obviously we want to have a consideration conversation around that to see if, maybe it's something where Invicta with a couple of additional nodes will service that type of I/O. We want to size the Invicta array properly versus maybe an Acela array if it's a tactical solution. But a lot of different ways we can kind of address that, and we just want to make sure that we understand, A, what the use case is, B, what kind of capacity concerns or constraints you have, and see what that pattern for growth might be, just so we put you in the right type of environment right off the bat and give you enough freedom around that so you can grow consumer to where your application needs to grow.
Perfect. Here's a good question. Are there any public-facing documents about cost savings to move from traditional spindles to Whiptail? Energy savings, network port usage savings, wear and tear savings, things like that.
Yeah, and there are a couple of use cases on our website that we've done white papers and customer use case analysis around. So definitely check out our website. If you don't find what you need, we've got a bunch in the in the queue ready to publish. So certainly reach out to the local sales team or any of the folks on the phone here today, and we'll certainly get you what you need for a lot of those different types of conversations, because it's a very popular conversation with lots of customers.
Perfect. What RAID levels are supported?
So we support 0, 1, 5, and 6. By and large, majority of our customers run RAID 5. We feel that it's really the best balance between capacity and performance for our arrays, because you still get parity protection, but you don't really have to give up a lot of capacity. So for something like a RAID 1 or a RAID 6, there are additional drives that you have to dedicate to parity. With RAID 5, it's just that single drive, and in a lot of cases, folks get into conversations around RAID 6 or for protection, or RAID 1 for performance. We actually get really decent performance and really fantastic performance. All the stuff that I talked about today in terms of numbers was on RAID 5. The RAID 6 conversation is interesting because usually that's with larger drive sets, larger RAID sets, and folks are concerned around, if I lose a drive and I need to walk every single other drive to reconstruct that RAID set, and it takes the better part of a day or a couple days with some of the huge drives available today, does that put the rest of my RAID set in jeopardy? Typical drive rebuild for us is in the span of maybe 20 to 40 minutes. So it's a very quick recovery process once you plop that new drive in.
Perfect. There's two I'm going to ask at the same time. What are RAID rebuild times, and can a RAID set span SSNs?
So just to answer the RAID rebuild time, between probably 20, 40, 45 minutes or so. Today, a RAID set does not span silicon storage nodes, and that's kind of a design consideration, just to make sure that we can guarantee performance availability and guarantee the performance envelope the way we've designed it at the onset. That's not to say that we may not look at other solutions in the future, but that's the way we've designed it today.
Perfect. How does your offering integrate with traditional arrays?
So we look just like any other LUN or any other NFS mount. So from the host perspective, it's really going to be pretty seamless. So if you've got a number of volumes attached to a host, maybe that's a Windows host, Linux host, ESX, whatever else it is for open systems, that's something where we're just going to appear like any other LUN. So in a lot of cases, we don't compete with the bigger storage vendors because we're really not in the same business as general purpose storage. Where we really want to be is that a specific part of the environment that is that tier 0 or very critical application that you're looking to really provide top-end storage for. So in a lot of cases, we're working in conjunction with their current storage offerings or other storage offerings. We're certainly not trying to replace them. What we're trying to do is really augment that storage capacity. And in a lot of cases, as we talked about, performance storage conversation is something where you're trying to stack with a typical hard drive storage array. You're trying to stack dozens, if not hundreds, of spindles together to get to an I/O perspective. If you can do that with a much smaller rack footprint and much lower cost per I/O, lower power per I/O, with something like Whiptail, then that allows you to open up that storage array for all the stuff that you were short stroking to really get to that performance number and get that capacity back. So in a lot of cases, our customers have bought one of our arrays and gone on and reclaimed a ton of capacity on their typical storage arrays by virtue of the fact that they no longer have to architect for these massive spindle counts anymore.
Sounds good. So far, you've only talked about write numbers or read numbers. What happens to IOPS in a say 80-20 mix read-write environment?
80-20 mix. Well, let's find out.
I love it.
Let's go 80 write and 20 read.
You're not going to guess. You're going to show us.
So it's about the same. I would suspect right now, and in theory the numbers go up, right? Because now you've got read and write mixed. I would suspect that I'm probably limited somewhere else in my environment, but we're already topping out a little higher in like the 220. So we gained back probably about 10,000 IOPS or so, which you kind of throw that around as a small number compared to what we're looking at. But in reality, 10,000 IOPS is an entire storage array or a couple of really, really hard-hitting applications for some folks. So you kind of have to put that in perspective. But as you start to look at mixed workloads, obviously, we try to architect for 100% write because with the read stuff, that's a little bit easier to come by for solid state. But it is certainly something where we can have some very pointed conversations around. And mixed workloads are probably going to get you a little bit better IOP performance because of the fact that read's very easy for us.
Very cool. He just replied, please try 80% read, 20% write.
All right.
This is on demand.
Yeah, and like I said, I'd love to go through my environment and actually have enough time to set it up correctly because we were suffering from the storm trying to get a lot of this stuff back, and some of our folks still are without power, believe it or not. So,
buddy, I live in Florida. I know about hurricanes.
All right, so about the same, but like I said, I think we've got some work to do in the lab because I would assume that based on the results that I'm getting, I'm also kind of wondering whether or not a couple of my demo VMs are actually sitting on the same ESX host or something along those lines. So yeah, like I said, this is one of those things where if you want to kind of turn the knobs and flip a bunch of switches for a specific use case, if you've got an application in mind, it's a perfect opportunity for an evaluation unit.
Cool. Do you have any customers using Invecta for video streaming?
So we do, and that's a really interesting use case because of the fact that the bandwidth numbers are so great on it, and it's certainly something it's really interesting. It's largely almost a holy conversation, right? Because we introduced Invicta, and the workloads that most of our customers run don't come anywhere close to what Invicta is actually capable of. So we almost put the cart before the horse, saying, hey, look, here's this system that allows a lot of customers to completely change the dynamic of how they think about architecting storage. So if that's the case now, and you never have to worry about I/O, what are some of the other applications that we could potentially use this for? Video streaming is one of those things. Certainly, intelligence, reconnaissance, a lot of data warehouse aggregation, data analytics. Those have been very, very interesting Invicta conversations for us, because they allow us to see how customers really want to use a lot of these products and figure out what's the best roadmaps for us to go down in terms of pursuing the next generations of these products and where we really kind of take the feature set.
Very cool. Well, here's somebody that seems like he's sold. Are there any migration tools or migration best practices to help consolidate storage and performance from other vendors?
Sure, and that's really, we take these largely on a case-by-case basis, right? Because there's so many different types of storage arrays out there. There's so many varied architectures. We have a subset of pretty popular use cases that we've seen really handy to use a Whiptail with, like databases, like VDI, like high-performance computing, things like that. But because the customer situations are so varied, I'd love to say that we've got a magical tool that we can just have you install and it'll automatically migrate everything. But the reality is, the architectures are so varied that we'll certainly work with you from a consultative approach to make sure that we do the best job that we can for helping you through that migration.
Perfect. Man, we are almost done. So does SSR support 2x NVR RAM cards, so there's no single point of failure?
So the SSR itself doesn't actually have any data in flight on it. It's only the individual nodes themselves. So everything within Invicta is really redundant in terms of, given a specific component, I can fail to multiple components and do a lot of very interesting things. But pull the plug on the SSR and you don't really have to worry about anything because I don't have any data in flight there. Each individual node really takes care of its own in terms of how it actually manages all the data on it.
Perfect. 2 questions left, and 3. One just came in. So when supporting multiple LUNs, will one LUN impact performance on another LUN, or will performance remain pretty steady?
Performance should remain pretty steady, right? So it really depends on how you actually structure that. And that's why we've got the virtue of multiple storage nodes. We've got multiple SSRs. So there's lots of different ways you can balance those workloads. But the reality is, if you've got two LUNs that are really really hot, the overall system performance is going to remain pretty steady. There's lots of different ways we can kind of look at to figure out, what's the best way to lay all that stuff out on a specific Invicta system. But keep in mind, I was talking about splitting hairs with hundreds of thousands of IOPS, and the reality is we've got a lot of customers that have pretty heavy workloads, but I haven't seen a customer yet that actually has enough to top out an Invicta platform.
Very cool. How many drives per shelf?
24. Yep.
Easy enough. Okay. How do you ensure data integrity? That the data returned by the SSDs is what was originally stored?
So we've got some very, very aggressive data integrity algorithms built into the system, and I'd love to kind of get into it on this call, but the reality is it's much, much better served by a whiteboard, and it's probably at least a 15-20 minute discussion just to kind of scratch the surface as to all the possibilities there. So I hate to kind of offload that question because we do have some very, very interesting stuff around it, but I would probably urge you to reach out to your sales team to get a more detailed discussion around how exactly this stuff works and how we protect the data. I mean, we talked a little bit about some of the strategies just around data in flight and the individual data layout strategies and how we can mirror shelves and all that stuff. But for the operating system itself, there are some more advanced things that we can talk about as to how we lay data out. But it's much, much better served by a whiteboard, just so everybody kind of understands the terms and the data process involved.
Perfect. And if they wanted to reach out to you guys and get a whiteboard, dive deeper, just contact sales?
Yeah, absolutely.
Perfect.
I live and die by the whiteboard in most of my customer engagements, and it's a really, really great tool for explaining exactly how a lot of these processes work.
Perfect. So last question. How many LUNs max can be supported on each system?
Geez, that's a really good question. I don't think I've actually tested the limit of it. You might have actually stumped me with the last one. Certainly in the span of hundreds, right? So it's a very, very large number. I honestly, off the top of my head, don't know what the upper limit is.
Okay. Well, we did it. We managed to stump them after, I think, the longest webinar we've ever done with the most amount of questions. So, Chris, I am very impressed. I very much enjoyed this webinar, and the guys out there that are still on the call and the ones that will listen to this in recorded version, I truly appreciate all the questions and your attendance and the time on and what have you. This has just been a truly educational experience for me, and I hopefully for all you guys. So what else do I say? Chris, I'll go ahead and give you the last word, and then we'll call this a webinar.
Oh, great, Doug. I mean, this has been a fantastic experience for us, too, because, like I mentioned, it's a very disruptive technology. We're very excited as to the possibilities that we've got around how we can help customers out with this type of technology, because it's one of those things where, if it's the what if. What if I didn't have to think about how fast my storage was anymore? What if I didn't have to depend on my spindle counts and how I architect all this stuff so carefully to make sure that my applications react the way I think they should? And what if that discontention issue really wasn't something I had to worry about anymore? How would that change the way I architect my applications? How would that really change the way I went about business? And those are the more interesting things that I love about this job. It's something where we can walk into a customer and say, here's what you could be capable of, and here's how all of your business processes could potentially change. If you've got a report that runs over the course of a weekend and we can cut that down to 20, 30, 40 minutes, how does that change the way you actually go about and create revenue? So those are the more really, really interesting conversations around Whiptail. And certainly the products speak for themselves. Certainly we can do a lot of different things around performance, but it's exciting. And the field itself is fantastic. I'm really, really proud to be a part of the Whiptail team because of the fact that we do so many fantastic things with these products. But thanks again for the opportunity. I mean, this has been fantastic. We typically get a bunch of questions at webinars, but certainly nothing like this. So I appreciate all the people that hung around for as long as they did. I appreciate all the stuff that you did, Doug, in setting this up, and I can't thank you enough for the opportunity.
No. It's the pleasure's all ours, truly. So on that note, again, thanks everyone for attending. If you enjoyed this webinar and sort of the format of the question-based and what have you, this is what we do on DABCC Live and our webinars. We don't want to preach to you. We want it to be an audience participation project, as I always like to say. And hopefully you found a lot of value in that type of format versus the typical, here's Chris going to preach to you. Although I think he could probably do that and make it interesting too. So on that note, guys, again, thanks everyone for attending. And to learn more, definitely hit www.whiptail.com. And of course, hit dabcc.com. If you guys want to follow Whiptail on Twitter, it's just Whiptail. So WHIPTAIL. And then, of course, you can follow me, Douglas A. Brown, on Twitter, and DABCC at DABCC. So on that note, I have nothing else to say. Thanks, everyone, for attending this webinar, and have a great day.